we are going to have a huge reactance as the series reactance itself in the equivalent circuit model, because I'm going to have the summation of the magnetizing reactance plus leakage together as the overall reactance. So if it is a generator, I'm going to have the induced EMF EF, which is due to the main field flux or the rotor flux. That is essentially EF, which is going to have a frequency which is decided by the rotational speed of the machine. Then we are going to have a value which is XS, which is actually a large reactance value which has two portions, one corresponding to the magnetizing reactance, the other one corresponding to leakage. So both of them are going to be there. Then we will have an armature resistance, which is the resistance of the copper winding which is sitting in the armature. Then finally what is available, this is going to be manifested as the terminal voltage, VT. And here is where I am going to connect the load. So this is going to be my electrical load as far as the generator is concerned. So I may call this as ZL. So depending upon whether ZL is going to be, inductive or capacitive or resistive, it is going to decide the power factor. When we actually drew the current in the phasor diagram, we specified as though the power factor is with respect to E, which is not really true, because we generally look at the power factor as the angle which is between the load current and load voltage, not really the excitation voltage. But just for simplicity, I started drawing like that. So let us try to take a look at the phasor diagram once again. So we drew the phasor diagram for the generator, which I want to specify once again. So this is going to be probably my EF. If I say IF is somewhere here, I should not specify this as IF, rather it is IF dash. So I'm going to have this as IF dash, which is the equivalent current on the AC side, which would have actually created a similar flux as that of what actually is the rotating flux of the rotor. The rotor is not having rotating flux electrically. It is because of physically rotating poles. So physically rotating poles creates a revolving magnetic field. If I had injected a three-phase current to produce a similar revolving magnetic field, what would have been the magnitude of the three-phase current on a per phase basis? That is what is IF dash. So IF dash is the equivalent AC current that I am visualizing, such that the strength of the magnetic field would be the same as that of the rotor magnetic field, right? So this is EF, and I am probably going to have my current which is somewhat like this. This is going to be IA, if I may call this as IA, or this is IL, same as, the load current. So this is the load current, and I am going to have clearly, with respect to load current, if I draw a similar vector in phase with that, that is going to be IA RA. And perpendicular to that, I should draw as IA XS. So when I add these two, I am going to get IA ZS. ZS is the synchronous impedance, right? So I would say ZS is RA plus JXS. So we call this as synchronous impedance, right? Now this particular IAZS has to be subtracted from EF. Only then I will get what is known as VT. So I can say that I have to just draw a vector which is probably in the opposite direction. So this is IAZS with the negative sign. This is going to be IAZS. So when I am looking at the resultant, this is going to be the resultant when I add EF to minus IAZS, and that is what is my VT. So this is going to be the terminal voltage VT. Right? So this is the case when I'm talking about the generator. So now if I look at it, between EF and VT, there is an angle of delta. I call this as delta. This is a very, very significant parameter in the case of a synchronous machine. And I am going to have this as the power factor angle. Because this is the phase shift between VT and IA. And this is what is the power factor angle. Originally what we wrote as the power factor angle is not correct. It is rather delta plus phi. What we got, originally what we mentioned as the phase shift between EF and IA, that is actually delta plus phi. Whereas phi is the power factor angle. And this VT invariably will be to the infinite bus. It will be connected to the infinite bus. When we synchronize the generator, VT will be actually connected to the infinite bus. So I would say rather VT is kind of set in stone. You can't change its frequency, you can't change its phase angle, if you may, magnitude. If you may take that as the reference, then I may say that VT is VT angle 0, whereas EF will be EF angle plus delta. Right? So normally VT is the voltage at the infinite bus, because of which this is taken as reference. So normally we write VT as V angle 0. So EF becomes E angle plus delta for a generator. Please clearly note that E is leading. It is going to lead the voltage VT in the case of a generator. On the other hand, if I try to draw a similar thing for the motor, right? I'm going to have basically, again let me draw, maybe this is what is my V angle 0. I'm starting with V angle 0. Okay? If I have V angle 0 like this, maybe the current drawn by the armature is going to be somewhere here, which is IA, and this is going to be my power factor angle phi. Okay? And in the case of generator, we said that EF is equal to VT plus IA ZS. This is what we said. Right? All these things are vectors. Whatever we are writing, all of them are vectors, phasors rather. Right? Whereas in the case of motor, when we talk about motor, we said that we are going to have EF equal to VT minus IA ZS. Right? So let us try to again draw what is the value of IARA. Probably IARA is like this. Now I am going to have IAXS like this. Now when I add the two, I am going to get, yes. Please note that the load impedance is the power that is being developed. We are talking about the drop within the machine. It can be a resistance, it can be a reactance, it can be a capacitance, it can be simply feeding the power to the infinite bus. It can be a motor, three-phase induction motor may be drawing a power from the generator. So I don't know what sort of load it is. So we are just not including the load impedance because we are assuming that that is the bulk power that is being transmitted to maybe infinite bus, maybe to the load, maybe to, whatever, whichever is the load system. Now this is going to be I'm sorry, this is going to be my IAZS again. So I have to draw the same IAZS in the opposite sense. So maybe this is minus IAZS, in which case I am going to get the resultant EF somewhere here. That is, when I try to look at V minus IAZS, I am going to get EF. Now this angle I may call as delta again, but please note EF is lagging behind the terminal voltage V. So generator and motor have this distinctive feature. This will distinct whether it is functioning as a motor or whether it is functioning as a generator. So if I am going to have EF leading, I can say the power is flowing from EF towards this side. This is the direction of power flow, right? Whereas if it is the motor, I am going to have actually, here is where my V angle 0 is, and I am going to have R and XS here. So this is RA, this is XS, and here is where my back EMF is, which is EF. So the power is flowing in this direction, right? So in the case of a motor, the power is flowing from the three-phase infinite bus into the machine. Whereas in the case of a generator, it is flowing from the machine back to the bus. So whichever is having a leading angle, that pushes the power in. Whichever is having a leading angle, in this case EF is having the leading angle. So EF pushes the power back to the mains or three-phase supply, three-phase infinite bus. Whereas in the case of motor, I am going to have this as the leading thing, whereas this is lagging. So I will be able to write this as EF angle minus delta. If I say V is angle 0, in one case EF becomes EF plus delta, which is in the case of generator. Whereas EF angle minus delta happens to be the phase angle in the case of motor for the excitation voltage, right? So whichever has the lagging angle, that is going to absorb the power. Whichever has the leading angle, that is going to supply the power. This is a very, very important characteristic in AC systems. In DC systems, the current will always flow from a higher magnitude to the lower magnitude. Whereas in AC systems, always the power will try to flow from a lagging angle, leading angle to the lagging angle. That is the way the power flow occurs. So if I am having some power requirement, for example in Delhi, and maybe I have local power generating stations, Badarpur and so on and so forth. But if I consider Delhi as a node and I want to take up power from somewhere else, I have to make sure that the power factor angle of the other side, from where I want to guzzle up power, that has to be at a leading power factor angle. So generally, we have to make sure of this in the case of AC power transmission. So many of the times, the control of the AC power transmission is through the phase angle control. Very often we try to adjust the phase angle and then make sure that sufficient amount of power flows, right? So this is one of the major differences between the generator and motor. So is this clear? The phasor diagram clear? If this is clear, let us now try to look at how to determine the parameters of the synchronous machine by making use of open circuit test and short circuit test, right? So let us try to take a look at that. And what is the power expression? These are the two things that I am going to do, and then we will call it quits, right? Okay, so let us try to look at open circuit and short circuit test of the synchronous machine. Open circuit test, I think I have already told, I don't need to specify it once again, because what we get from here is the open circuit characteristics. So what we try to get is variation of EF. I have just changed EG to EF because I am now calling it EF throughout. So variation of EF with respect to IF. That is the field current. Right? This is the generated voltage in the armature under open circuit condition, of course. So I am not connecting any load to the armature. There is no question of any armature reaction and so on and so forth. So what I am going to do is something like this. I have a prime mover. I am showing it in the form of a DC motor. Okay, because this is what we use in the laboratory. So I am exactly showing it like what we do. So maybe it will be a separately excited DC motor, it doesn't matter. And I am going to apply the voltage, say 220 volts DC. Of course, I will have a starter. I may have a rectifier, I may have large resistance, whatever. But I will have a starter along with the DC machine. And I do have a field. So field will also have a resistance so that I can adjust the speed to exactly 1500 RPM if it is a 4-pole machine. I can adjust it to 3000 RPM if it is a 2-pole machine. Right? So this is going to be my prime mover. So this is the DC motor which is acting like a prime mover. Only thing what I will measure here is to make sure that the speed is 1500 RPM if it is a 4-pole machine. Nothing else is needed. I don't need really the field current or anything here because I'm not concerned about the DC machine's characteristics. Right? Now this is going to be coupled to a synchronous machine which is having the rotor. So let me show the rotor somewhat like this. So this is the rotor of the synchronous machine. And maybe I have the field here. This is the field. Now this field also has to be connected to a DC supply along with an ammeter, so that I am able to exactly measure how much is the field current that is flowing through the field of the synchronous machine. So I am going to have, let us say this is my DC supply which is 220 volts DC, and I am going to have say plus here and minus here, and then I am having a potential divider. So this I am connecting here and this I am connecting here. So I am applying a variable potential to the field. Right? This enables me to get either zero field current or I can go to maximum field current. That's what is going to happen. So I will put obviously a DC ammeter here. Right. Now this is actually going to have the armature now. So this is the armature and it is open circuited, and I am going to put a voltmeter here. And I have to only make sure that I run it at a particular speed which is corresponding to synchronous speed. That's about it. Nothing more than that. So I keep on increasing the field current of the synchronous machine, and then I note down what is the voltage generated. So I am going to get essentially a characteristic somewhat like this. So this is EF. So I am measuring EF and I am going to have IF. So this is in amperes, of course this is in volts, and then I am going to have a characteristic somewhat like this. So this is what is my OCC. Right? The next test that we are going to conduct is the short circuit test. Yes. Yeah, this is the coupling. How will you drive the synchronous machine otherwise? You have to rotate it. I don't have a turbine. I'm using the DC motor as my prime mover, right? So it is providing the mechanical power input so that the synchronous machine works as a generator, right? They can reverse the role very well. If they have to reverse the role, they'll do that very nicely, okay? So if I provide three-phase supply to the synchronous machine, it will work very beautifully as a motor. There is no problem. In that case, DC machine will work as a generator. And then I can connect a load. That's not a problem. Rather than connecting a DC supply, 220 volts DC, I can remove that and connect a load, resistance load. Rotor will have to get definitely a DC supply no matter what, whether it is functioning as a motor or generator. The field has to be excited. I don't know whether I answered your question, but the speed is decided by the frequency now. If it is working as a motor, if it is a synchronous motor, the speed is decided by the frequency. So if I connect it to 50 hertz, no matter what, if it is a 4-pole machine, it is going to run at 1500 RPM. You can't make it run at any other speed. That's it. It's set in stone. If you are changing the frequency, you will get a different speed. So synchronous motors are essentially constant speed motors. They will not even have the small variation what is seen in an induction machine. No way. There will not be any change. So if I want to have speed control, I have to have frequency control. No wonder we have become a very important commodity, power electronic engineers, who make inverters, who basically generate variable frequency. So all the synchronous motors are now able to run at variable speed if I am able to generate variable frequency. That's the reason. Okay? So in short circuit test, what we are going to do is, everything else remains the same. Only thing is, I'll make sure that first of all, field of the synchronous machine is brought to a minimum. I will have to bring it to a minimum, because with full voltage, I would not like to short circuit the machine. And generally what we try to do is to have a switch connected here, because we don't want to again start the DC motor from 0 speed, bring it up to 1500 RPM and so on and so forth. Very often what we do is to provide a 3-phase switch here. And then we will try to short circuit this switch. We will close the switch once open circuit test is done. After open circuit test is done, we will keep the switch open, do the open circuit test. After open circuit test is done, what we will do actually is to minimize the field current of the synchronous machine. So after minimizing the field current of the synchronous machine, then short circuit the switch or close the switch to short circuit the armature terminals. So I have 3 terminals of the armature which will be short circuited automatically by using this 3-phase switch. Okay. So let me say this is maybe TSW1, 3-phase switch 1. Okay. So this is TSW1 will be closed. Of course, I should have had an ammeter here. At least in one of the terminals, I should have put an ammeter, because I would like to measure the current, short circuit current of this machine. So when I actually measure the short circuit current of the machine, I don't want that current to go beyond the rated current. I have short circuited the terminals of the alternator, and I am still allowing the alternator to generate, because I have provided some minimum excitation, maybe hardly any. I will slowly increase it. As I increase the excitation, this current will go up. If I may call this as IA, this as IF, IA will go up as we increase IF of the alternator or synchronous machine. I hope you understand this. I am running this still at 1500 RPM. If I increase IF, I'm going to increase the generated voltage. If I increase the generated voltage, clearly this current will go up. So I don't want that current to go up beyond whatever is the rated value. So if I know the rated value, I have to make sure that the current is limited to the rated value, nothing more than that. So maybe I am going to get, maybe I'm just showing the rated voltage somewhere here. It may be higher. I'm just showing for the heck of it. So this is my rated voltage. Maybe this is EF rated. Line to line voltage, let us say it says 400 or 415, 460, whatever. That is going to be the rated voltage. So this corresponds to IF rated normally. Right? As far as the short circuit test is concerned, I will again plot with respect to field current, what is the variation of the short circuited armature current, right? So I will have a current scale also. Very clearly, I should have two scales. One is E, the other one is IA. Both scales have to be there. So let us say with respect to IF, I am going to get probably, you know, short circuit current at rated value is somewhere here, below that or here. So I'm going to have something like this as the variation. This is the short circuit characteristic. So this is IF versus IA. This is IA1 for IF1. This is IA2 for IF2 and so on. So this is what is going to be the variation. So this is SCC, this is OCC. Open circuit characteristics and short circuit characteristics. So I have got both the characteristics. Now at rated value of field current, which is corresponding to rated generated EMF at open circuit condition, I would like to measure what is the current and what is the total voltage. So this is voltage, whereas this is current. So get current at IF rated from SCC, voltage at IF rated from OCC. So I have got both. So let me say this is IASC. Let me call this as EFOC. So I can call ZS is equal to EFOC divided by IASC. When I am having rated excitation, if I am getting a particular value of voltage under open circuit condition, had I short circuited the machine at that point itself, only impedance which is actually limiting the current is its internal impedance, nothing else. Are you getting my point? Let's say my rated field current is 1 ampere. At 1 ampere, my machine is producing 400 volts line to line voltage, which is the rated voltage. If by chance I apply the same 1 ampere of field current to my alternator when it is running at 1500 RPM and I have short circuited the terminals, the current that is flowing will correspond to whatever would have been the short circuit current, right, under rated voltage condition. This is under rated voltage condition. So the current is limited only because of the internal impedance of the armature. So at rated condition, if I am able to measure short circuit current, and at rated condition, if I am able to measure the open circuit current, open circuit voltage, the ratio of these two indirectly gives me the synchronous impedance. So synchronous impedance is going to be the ratio of the current obtained under short circuit condition at rated IF. And I'm going to look at what is the voltage generated under open circuit condition with rated IF. The ratio of these two will give me basically whatever is the value of synchronous impedance. Yes, Sankalp. Let me draw the graph once again here. This is my characteristics. Let me show two axes. That is better. Right here. So this is my origin. Okay. So this is going to be maybe voltage axis. And this is going to be current axis. Okay. So I have two axes. And I'm going to have IF. Okay. I am first drawing the voltage characteristics. So it will go like this. Probably. This is what is actually OCC. Right? Let us say this is the rated value of voltage, probably. So I am going to say that this corresponds to IF rated. Right? Now, I am trying to now look at the short circuit characteristics. So I have to first of all look for the point at which I am going to get rated armature current. Slowly I am going to increase IF. I am going to plot two things. One is voltage under open circuit condition. The second one is armature current, IA, at short circuit condition. This is voltage under open circuit condition. So that is the reason. So this is corresponding to the red color axis. So this is actually the rated voltage that I am talking about. So this is the rated voltage, maybe 400 volts or whatever. That is the rated voltage. Some books show it on either side of the graph. Anyway, it is the same. We are plotting two graphs in one particular plane. That's it. Okay? The other one, what we are looking at is the short circuit characteristics. For short circuit characteristics, I have to see where maybe IA rated is being reached at what IF. So maybe this is IA rated. If I try to extend it here, this is what is IA rated. Okay, so this is getting joined here. So I can draw this as the short circuit characteristics. This is passing through this point. Please note, short circuit characteristics is linear, open circuit characteristics is involved with saturation. Okay? So I am going to have now, because I have drawn it like this, I can always get what is the IA value at IF rated. Let me call this as some AB. Let me call this voltage as CB. So CB is the voltage at IF rated. AB is the voltage current at IF rated. So I'm going to say that ZS is equal to CB divided by AB. That is what is ZS. I want you guys to note one thing clearly. Yeah. I am looking at what is the rated value of field current at which voltage is produced under open circuit condition. Under that condition itself, had I short circuited my machine, what would happen? A current would definitely flow because I have short circuited. Until now it was open, so there was no current flow. The moment I short circuited, there will be a current flow. That current flow would have reached infinity if the internal impedance of the machine had been 0. It is limited to a finite value only because of internal impedance of the armature. So this is giving me a way to measure the internal impedance. So if I know what is the current that is flowing under rated condition, that will actually, rated field condition, that will give me a way to determine what is the internal impedance of the machine. That's what I'm precisely doing. Right? So the open circuit characteristics and short circuit characteristics basically are done mainly to get the synchronous impedance value of the generator. Yes. Armature line to line. I can always say, okay, let me draw this is per phase rather than this. If it is against star and delta. If I measure the current current also, phase current, and voltage also per phase voltage. I can measure both per phase. Very good question. I was expecting this question. Why is the current not following the voltage? Right? That we'll have to definitely answer. What he is saying is, if the current is essentially voltage divided by Zs, the current and voltage should have followed the same path. Doesn't make sense, right? To have two different paths, right? Please remember what we talked about the magnitude of the impedance, right? We said this is Xs, this is R, and Xs is much, much higher than R. So this is highly inductive in nature. The current is going to be highly inductive. It is going to be almost lagging behind by 90 degrees. Am I right? So let us say I have my IF here. I am answering the question of, I am reiterating. Voltage divided by the impedance is current, and the voltage and current should follow almost the same trajectory. You can't have two characteristics which are entirely different. Why are they different? We are just answering that question. Okay? So if this is IF, I said that EF is somewhere here. EF is somewhere here. Right? This is IF dash. And this is EF. If I am going to have a current in the armature which is highly inductive, I am not having any external impedance. Only thing I am having is Xs and R is negligibly small. Xs is way too large. So I have short circuited this and I have connected EF here. This is what I have done during short circuit condition. Now I am going to have IA probably as lagging as this. Okay? Maybe quite large. Now IF produces phi F, which is the main field flux. IA produces a flux which is corresponding to armature. So I am going to have one of them as phi F, which is probably in phase, and the other one as phi A, which is in phase with IA. What will be the summation of these two? It will be minuscule. It will be really minuscule. Try to add these two. So I have to essentially draw a parallel vector to this. So I'm going to have something like this as the resultant. So this is phi A and this will be the resultant. Whatever I have shown as the small vector will be the resultant phi. So under short circuit condition, the flux that is remaining in the air gap becomes really, really small. Because of which I am going to see that the machine never tends to saturation. Never ever under short circuit condition of an alternator it will go to saturation. It will not go to saturation because the armature flux and the field flux are literally in opposition to each other. Literally.
Why only under short circuit condition?
Under short circuit condition I am not having any load here. Otherwise I will have a load here which will determine the power factor. Here is the power factor of the machine roughly. This is the power factor. Right? So this power factor angle happens to be almost close to 90 degrees because of this reason. If I connect a highly inductive load at this terminal, it will almost behave the same way. Highly inductive load if I connect here, it will almost behave the same way. So RA and XS essentially behave like pure inductance. That pure inductance is going to make the current lag behind almost by 90 degrees. So these two oppose each other completely. And because they oppose each other completely, literally the armature flux tends to kill the main flux. So you are going to have very, very minimum amount of flux under short circuit condition, and that is the reason. So I have short circuited but I'm getting the rated current only beyond IF rated. Normally in the transformer, if I apply rated voltage, the transformer will burn. But here I am applying IF rated. It is generating rated voltage and I am going beyond that. Right? I have come from 0 to IF rated. I have minimized the field. When I started the short circuit test, I have increased it slowly. It has come to IF rated. After IF rated also I have to go a little more. Only then I am getting the rated armature current. See, this is IF rated. I have started from 0. When I came to IF rated, I was getting E rated under open circuit condition. This IA is under short circuit condition. Because the flux gets minimized tremendously under short circuit condition, essentially even the voltage generated somewhat is compromised. The voltage generated also becomes compromised, because of which to actually pass rated armature current, I have to increase the excitation further. It was under this excitation when I was at rated value of EMF under open circuit condition. But what I am getting as armature current is not even IA rated. IA rated is somewhere here. Whereas this is the current I was getting under rated excitation under short circuit condition. I am not getting even that much. So I have to increase the excitation a little further because the flux has been, minuscule, very, very small value, because the armature flux opposes the field flux completely because of the 90-degree power factor angle, lagging power factor angle. On the other hand, had excess been capacitive, which is imaginary, it is not going to happen. I am just saying hypothetically. If the excess had been capacitive, these two would have aided each other. Absolutely. We would have gone way beyond saturation. Very, very huge amount of, flux. If the saturation had not been there, you would have seen a huge amount of flux. That's one reason why whenever you connect a capacitive load in a synchronous generator, again, we talked about this in transformer. When we connected capacitive load, we had negative voltage regulation. Right? At no load, if you had 230 volts, at full load capacitive, you would have 240, 250, 260 volts, whatever, depending upon how much current you have drawn. The same thing holds good in synchronous generator as well. If I am going to have a leading load, I can have the voltage regulation to be negative. If I have a lagging load, the voltage will plummet. It will really go to lower values. If I am connecting it to infinite bus, how can the voltage go to lower values? It cannot, because the infinite bus would say, you better maintain this voltage. So what has to happen is the generated voltage has to be increased. There is no other way. I repeat it. Infinite bus voltage is, let us say, 400 volts. Okay? If I am having huge amount of synchronous reactance in the machine and the current drawn by the loads in the grid are all lagging, the voltage might try to go from 400 to 300 or 360. It will plummet. It will go down. But infinite bus is going to say, you can't have lower voltage. It is not possible. If you can't have lower voltage, only way is to increase EF. So, increasing EF will be done by adjusting the field current. This is done all the time in the power stations. It's generally known as AVR circuit, automatic voltage regulation circuit. Automatic voltage regulation. Right? This is done very often in most of the power stations, depending upon what kind of load the grid is facing. If it is capacitive load, I have to reduce the excitation. If it is inductive load, I have to increase the excitation. This is done very repeatedly. I don't want to go into power expression. I think it will become too much. We'll wind down with this, saying that what all we did in this course. And with that, we'll conclude. Yes. See, one thing is, you have to understand first of all that in the transformer, there was something called a primary which was drawing the current. And that current was reflecting onto the secondary side most of the times except for open circuit condition. So you had at least some current to measure. And the voltage what you measured on the secondary side is a reflection of the primary voltage. So what you are measuring are congruent, they are related to each other. It's not that they are completely, unrelated. Whereas here, if I try to measure the field current, that is not going to really give me an index of what is the impedance or the current that would have been drawn by my armature. They are disconnected circuits completely. And you can't even say the current carried by the armature is going to get reflected onto the field. Not at all. Not at all. It absolutely depends upon what is the amount of load that you have connected. The current will only depend upon that. And to supply that load, I should have given sufficient amount of mechanical power from the prime mover. That's all it is related to. The field is only working as a wire media. It's a facilitator. It is definitely not giving any resources. It is only a facilitator. So, you can't really take the field current as the current which would reflect on the impedance of the armature. That's not possible. The same way, in the short circuit condition, obviously the voltage that I would measure across the terminals of the armature will be zero because I have short circuited. So, I don't have a way to measure the armature voltage. So, that is the reason it's a very, very beautiful method, whoever has devised it, to get what is the voltage that would have been generated in the armature under open circuit condition, vis-a-vis what is the current that is being drawn by the armature had it been short circuited with that kind of generated voltage. So, very clearly, there is a huge amount of difference between transformers circuits and synchronous generator circuits. The equivalent circuit as well as the way it is being analyzed, right? So that is the reason why they are quite different. Okay?